Today we're going to continue to explore functions in the Cartesian plane. Last week we looked at the function 2 times x minus 3, and then we replaced the 2 with m, the slope, and changed the values of m to see what would happen to our plotted line. So this week we are going to explore the function a times x squared using various values for a. So the first thing you want to do is plot your function. So you're going to go to Graph, Plot New Function, and we don't have a value for a, so we're going to set one up. You're going to go under Values, New Parameter, we're going to name it a, and we're going to leave the value at 1, so click OK. Then we're going to do times x, and then we use this little guy for our exponent, 2. Okay. So you'll notice instead of a line we have plotted a parabola. So let's see what happens when we change our value of our parameter with our parabola. So you want to highlight your parameter and double click, and let's start with a higher number, 5, enter, and you'll notice that the parabola closed in on itself. It's still facing upward and it's still opening upward. So let's see what happens when we type in a smaller number. Let's do 0.5, enter, and now our parabola has opened wider. So let's see what happens when we do a negative number. Let's do -1. Now our parabola has opened downward. So we see that this function, by changing the value of a, allows us to make the parabola close or open upward or open downward. So let's just punch in the same numbers we had earlier, and we'll do -5. So we're still opening downward and it's closing in. And then if you do -0.5, not -5, -0.5, then it opens up again. So what happens if we put in 0? 0, it looks like it's disappeared, but if you'll notice here, it's actually plotted on the x-axis, because you can see the arrow here. Now, from this plot, I want to animate, because this will actually show your parameter of your parabola by changing the values of a. So we're going to highlight our parameter, and we're going to display, and we're going to animate parameter, and we're going to really do it this time. And notice that it goes up, and you can change the direction, and then it comes back down. So changing the value of a affects whether your parabola is open or closed, and it also affects whether it's facing upward or downward. So I'm going to pause this, and then I like to undo, because sometimes it messes me up if I don't. And then we're back on 0. So from here I want to use the plus and the minus keys. So we're going to use the plus key first, and we're going to do it right. Start at 0 there. Highlight your parameter and then plus the plus key, and notice your parabola goes up, and when you use the minus key it goes back down. And this was kind of what our animation was doing also. So from this point I want to create a family of functions to see kind of all of the plots that I can get. So I want to highlight my parabola or my graph, make sure my parameter is highlighted, construct family of functions, and we're going to do the same as last week, 31 samples, a domain of -10 to 10, and click OK. So here's the parabola that we originally had, and then here is our locus. And notice, if you notice from last week, when you did the plot, the family of functions, where hide, show, all of the lines crossed at the same center point. So let's look at the parabola and see what's happening there. And they all have the same center point as well. So let's do an animation here, and we can actually watch the parabola go in and out from our family of functions. So we're going to highlight our parameter, and we're going to animate the parameter, and then you can watch it go all the way into the domain that you have set, and then reverse it, and you can see it come back out. So that is what happens when you change the value of A, your parameter, on a parabola. And then just for fun, I read somewhere that the points in the plane of a parabola are equidistant from a set point and a set line. So I wanted to, it's really hard to talk and think at the same time. What am I trying to do? I'm trying to hide this. Hide. So I wanted to see if I actually have a parabola here. So what I did was I decided this is going to be my point, and then the x-axis will be my line that I'm trying to see if the points on these two lines are equidistant from this point and from this line. So first thing I want to do is make sure I get the points exact on this parabola. So I want to make a parallel line run through it. So the first thing I want to do is set an arbitrary point here on the y-axis somewhere, and then I'm going to highlight the x-axis and the point, and we're going to construct a parallel line. And then to get the points, I'm going to highlight the parallel line and the parabola, and I'm going to construct intersections. So now I'm going to measure these coordinates. The points are already highlighted, so I can go to measure, and I'm picking coordinates, and I can see here that my y coordinates are the same, -6, -6. And then if I look at my x coordinates, they are also the same. One's negative, one's positive. As far as distance, they are the same. So we have proven that this is a parabola. And just for kicks, let's see what happens when we change the value of A. What happens to our coordinates? So let's change it to 5. I'm sorry, -5, because we're working down. -5. And we notice that the y stays the same and the x changes. And let's see what happens when we say -0.5. And they stay the same as well. The y does, but the x changes. So I just thought that was interesting. Miss you guys. See you Friday.